right, so now I'm going to the Future Day presentation. Okay, so the title, The Shape of the Future in 2050, Solving the Unfixable Problems of the World with Multifaceted Narrow AI and Youth Creativity, Creating a Positive Medical Future for Everyone. Most of the slide set was put together by Ishita Mogi, and so that there's good collaboration between the two of us. She is not here at the moment because this is a busy day for her. But two surprising facts about us. We're big fans of Yuval Noah Harari, but we also disagree with his assertion that no one knows what the world will be like in 2050. That assumption comes from considering humans as the only actors. And if you factor in multifaceted narrow AI, then predictions about 2050 can be made. The second surprising fact is Ishita and I are not unlike you, the audience, but we have had surprising success changing things online since 2018. It's hard to find evidence for the other side of the argument for a lot of the things that we changed. And hard to see that they were ever different from the way they are now. And if we could do that, so could you, because we are very much like you. And so that's what we mean by agency, that you can do the things similar to what we have done. So our first objective of the talk, show you that one person has more agency than ever before, can bring about bigger change and faster than ever before. COVID has reset everything, creating enormous opportunities. And you can hear a lot of people talking about the future now as if the only actors were human actors and human institutions. And oh my goodness, what will humans do? What should humans do? What should human institutions do? What should government do? And I don't think that's the way to look at it. You need to consider sentient AI or narrow AI as another actor here. And when you do that, you can see going back really 20 years, what the influence of AI on our daily lives is. You can look at this video, which I reposted recently, but it's from 20 years ago, 2001, when I had on my computer Aaron Artificial Intelligence Painting Screensaver, which creates unique art right in front of you as it's saving the screen. And this was capable of pleasantly distracting one of the most insightful tech leaders ever in Canada, Sarah Diamond. She founded the Banff New Media Center and for 15 years was the president of the Ontario Institute for Art and Design. She's won the Order of Canada. She's just done about everything that a highly capable person in Canada can do. And yet you'll see on the video, not only did she say she couldn't really compete with this, but she was happy about what the screensaver was doing, as the audience was. This wasn't an irritating distraction, but a pleasant one. Then 10 years ago, you can see Sony Aibo robotic dog, capable of being a video presenter. And here I have the 2021 version of the Sony Aibo dog. And recently, DeepMind AlphaFold's success in solving protein folding shows how narrow AI can solve important problems humans could never solve alone. Global warming, nuclear war, male versus male aggression. And now you probably thought that we were just going to keep showing that slide set forever, but just to show I'm full of surprises, I'm now going to do a part of the presentation from virtual Zoom backgrounds. So this is a depiction of narrow AI, things AI can do that is easily distinguished from the other things that AI can do. It's not general AI, but narrow AI. And it is the surprising success in the area of protein folding, where drug design, computerized drug design, is much easier now in 2021, now that protein folding has been solved by DeepMind AlphaFold. And that's not something humans could ever have done on their own. It's way too complicated. Just like climate change, and global warming, and nuclear war, and male against male aggression. All those things are things that humans on their own can never solve. But with narrow AI, I think they could be solved relatively easily, just the way that protein folding has been solved. And it really means that we are looking at a very positive world, because we have an entity to help us with all these difficult problems that it seems like humans cannot solve on their own. And it's kind of funny, Yuval Noah Harari's assertion that no one knows what the world will be like in 2050. Go into Shutterstock.com and just search for images, just with the search being 2050, just put in 2050, you get lots of graphics like this of highly specific predictions that Shutterstock is making about 2050. Of course, what I'm telling you is this will not happen if we actually factor in narrow AI and the help it could provide to us. And if we do that, then we can have a much more successful outcome for the human race. Yeah. So anyway, Simon's here now. So what I would suggest is, why don't we start talking about quantum biology, and then we will go back to the slide set for Future Day later on. So Simon, welcome.
Hello, sorry being late. Sorry about that.
That's okay. So as I was telling the students, we have this interesting arrangement where you are going to manage the teaching in quantum biology, but Jack Tuszynski is in the background in several senses. We're using his videos for the teaching, and there are many choices for that. The students can try to do it all in one video, like the most popular video ever from the course encapsulates all of quantum biology in one 80-minute time period from 2014 that has 7,000 views. After that, we did an international peer review on the course, and the recommendation was that that lecture has much too much stuff in it and that we need to divide it up into multiple lectures. So the students will have their choice of how they wish to do it. And we have 3 sessions then where you and I and they are going to talk about quantum biology. One is today, one is Thursday, and then next week is going to be medical ethics, because Dr. Van Manen found that as a convenient time for him to teach. And then after that, so like 2 weeks from today, we'll do the final session on quantum biology. So the students get a lot of time to ponder quantum biology and to take it in their own pace to figure out how important it is in their lives. If you think about this course and kind of being on the cutting edge, I think quantum biology really is something that you're not going to find in any other course. So it's really, in a sense, more out there than anything else that we teach. And if you combine that with the quantum supremacy talk. So Simon, do you want to say some words about your feelings and thoughts about teaching quantum biology?
Well, for starters, I think quantum biology as a name sounds very advanced and like completely out of the ordinary. I especially love teaching this part of the course because we get to talk about all the fun, interesting, like kind of thought experiments, and we don't have to go into any of the math at all. So I think that's the most fun when we talk about these things. Because once you look at the math, it's not fun anymore.
Yeah, I think that's absolutely right. Quantum physics is very hard, but when you really take a course in quantum physics, you have to be doing the math. And in this course, you don't have to do that. So we're just dealing with the overarching principles. There are a few math facts you need to know, like how many watts the human brain is, stuff like that. But relatively few facts that we're trying to teach you. We're trying to teach you concepts, and I'm very proud of this part of the course. So you may wonder why that video got 7,000 views. Jack Tuszynski was a visiting professor at IBM headquarters. And before he came, the people there were looking at this video. And I think it has a part at the end where he says, all the textbooks will be rewritten, that basically quantum changes everything. And the people at IBM were so inspired by that they asked all their people to watch that part of the video. So that's where part of the 7,000 views come from. But really, it's a great privilege for us to be teaching you content of this type. It's not necessarily more interesting than anything else we teach, but it's equally interesting to what other candidate you would bring for really interesting content. I think it's a really interesting area. And in the same sense that IBM was excited about the fact that all the textbooks will be rewritten, you can also be excited about that. By learning about quantum biology, you're learning about something that's really going to change everything. And yeah, so that's part of the excitement. Simon, back to you.
Right, right. So, I'm gonna go through Jack Kaczynski's quantum biology last lectures, and they're actually quite intense. Even I'm sure he included like 1% of what he actually wanted to say because it's already dumbed down, but it's still pretty intense. So yeah, I'm gonna split up this lecture into 2 sessions. So the lecture in total has over like 200 slides, and we're certainly gonna skip over a few of them. But today we're gonna go into a quick introduction about the physics world prior to quantum mechanics. And then we're gonna talk about quantum mechanics, its basics. And then we might get into a little bit of quantum biology today. But the second lecture will mostly be on quantum biology, how quantum mechanics can be applied to biology.
Great.
Okay, so should I share my screen, I guess?
Yep.
Okay, okay. I might have to leave the meeting right now because apparently I need to like get a permission or something.
No, you don't. I don't think so.
I think let's see.
Let's see. Maybe I need to make you co-host. Let's try that. Make co-host. And if that doesn't work, then I can make you host. But now,
Okay. I think it's actually like this computer has said like Zoom will have to restart because I'm allowing their permission to share the screen. I'll be really quick.
yeah, fine.
Okay.
Yep. No, you can go away and everybody will say, where did Simon go? And then you'll come back. Yeah, that's fine. So Ching, what is it like being here finally with the class? Is it less exciting, more exciting, the same as what you expected? Or
All
Well,
right.
I mean, it's really nice to see everyone. I was sort of part of the class, but in a sort of unsynced way because I would be watching the videos and following along. So it's nice to be part of the action, and I just like the way that the course material makes us think in new ways. So thanks, Simon, for being here today.
yeah, so you know that I share my office with Rebecca Hu, and Cheng's name is on the door too. And there's a shelf in here for her. And there are cutouts of her that she's actually in Montreal. And we're thinking that Taryn Stokowski will also have a shelf here. So there are various ways in which people can be actually in my office or just virtually in my office. So, but Ching is a very important part of this course and it's been helping me for a long time. Okay, Simon's back. Yep.
Right, here we go. Okay, can you guys see my screen?
Yes.
Perfect, perfect. Let's see how we enter presenter view.
There you go. Yep.
Okay. Okay, so here we go. So before we discuss quantum mechanics, I just want to go over really quick, other scientists and their contributions before quantum mechanics. So at the very start, there was classical mechanics. And when we think classical mechanics, we usually just think Newton and his like force equals mass times acceleration, blocks on blocks, gravity. And then we have electromagnetism, which is when we bring in the relationship between magnets and the flow of electrons. So that's electricity. And then we get into thermodynamics, which is talking about, the first and second law of thermodynamics. There's no such thing as a perpetual machine, and that energy can't be created or destroyed. And then most recently, there's been statistical mechanics. So near the end of the 19th century, this famous scientist, Albert Michelson, said that it seems probable that most of the grand underlying principles have been firmly established. The future truths of physical science are to be looked in the sixth decimal place. What this means is all the macroscopic world, this scientist thought at the time to be firmly established. Everyone seems to know what's going on, but it's at the sixth decimal place, meaning, at the nanometer level where scientists had yet to make any discoveries. So we just talked about the 19th century scientific revolutions. So in the 20th century scientific revolutions, this is what we see. So, Einstein's special theory of relativity, general theory of relativity. When you think of those theories of relativity, just think about, especially the general theory, just think about his space-time model, how he proved that gravity was actually a distortion of space-time, and that's what caused gravity. And then here we see the third bullet point, quantum mechanics by these leading scientists, Max Planck and Erwin Schrödinger. And then we get into, after the development, those are physics developments. Then we get into quantum chemistry, quantum field theory, and then last two, which is most exciting, which is, and not many people think about, which is how quantum mechanics can be applied in the biological sense. So in the last 120 years, we have classical physics, then quantum physics, then quantum chemistry, and now we get into very interesting things in new fields such as quantum physiology, quantum biology. Is there such thing as a quantum brain, quantum anesthesiology, and quantum psychology? These three things with the question mark we'll definitely talk about in the second lecture. So we're gonna go through the classical sense of, let's move this over here maybe. Let's talk about the classical sense of physics before we go into quantum physics. So for example, we have a blue ball falling and it has a bunch of properties, right? We know its mass, which is how heavy, how much material is in this ball. And then we know 4 coordinates about it, right? We know its XY position, we know its depth position, and we know its time right this moment. And then we know its velocity, which is its speed, as well as acceleration. This is a particle. Now, if you look at a wave, it's very different. So they don't have an exact position because they oscillate through space and time, although they do have a direction of travel, which gives us a velocity. And its strength, or as we call it, its amplitude of the wave, is defined by the length from its top and lowest position. So let's talk about the differences between particles and waves. So for particles, when particles hit each other, they have 2 options. They can hit each other and shatter, or they can hit each other and bounce away from each other. But waves are different. When waves hit each other, they can be destructive, or they can interfere destructively or interfere constructively. These days we have so much noise canceling headphones. It's work in that way, right? They exactly match the opposite frequency of what we hear, so they can cancel out all the noise. And so let's look at some key differences between waves and particles. So waves, when you shoot out a wave, it's not like throwing a ball. The moment you release a wave, it'll spread out indefinitely. And because because waves aren't particles, they can interfere with each other. Whereas a particle, if I throw a ball, that ball's not going to split into many other balls. It's still the same ball that's going to move through space. So why was there a need for quantum physics? And there was a need because there was phenomena in this world that couldn't be explained by the current theories. And that's when scientists, push to get newer theories and models. So here's just a list of phenomena that classical physics really couldn't explain, right? Atomic emission absorption line spectra, the electron configurations, we learned so many of them as a kid. It went from the plum pudding model to some really cool like nucleus model, and then there's a Lewis model, then there's a Bohr model, like there's always just new models to describe electron configuration, but none of them are perfect because all of them work in very specific scenarios. Black body radiation, photoelectric effect, that's Einstein's Nobel Prize contribution, specific heat of solids, and quantum scattering of X-rays. So what's quantum theory in its essence? There's a lot of words. I want to break it down for you guys. So the point is, in quantum theory is that everything has discrete states. And what discrete means is it's like a ruler. When you try to measure a table, it's not infinite decimal places. Discrete means that the ruler has discrete states. So it's 1 centimeter, 2 centimeter. So, quantum theory goes off of that. People might assume there's like no limit to size, but quantum theory states there's always the lowest possible amount or lowest possible size. So that's one of the essences of quantum theory. And then another thing is that in quantum theory, things aren't definite. So although it's definitely true that my index finger is right here, in quantum theory, it's more probabilistic and not deterministic. And so to accentuate these points, Einstein said, like, God does not play dice. Einstein was against it, right? He didn't think that the microscopic world, things would be so probabilistic. He was used to things being more definite and more predictable. And then Feynman said, things on a small scale behave nothing like things on a large scale. I hope you can accept nature as she is absurd. So Feynman was, understanding of the quantum effects here. And then Bohr said, anyone who is not shocked by quantum theory has not fully understood it. So, just to point out how really unintuitive quantum theory can be sometimes. So what are the basics of quantum mechanics? So again, we said that classical physics, when you think of classical physics, think macroscopic events, things we can see. That's the macroscopic world. That's classical physics. And where does classical physics takes us? Well, classical physics takes us to the moon, right? Classical physics takes us to Mars. So it's very useful. Like the still basic principles of classical physics still enables us to do all the macroscopic things we have in this world. Quantum mechanics really comes in to describe microscopic phenomena, things we can't see, such as your photo atom scattering, and like how the electrons flow through our computers and mobile phones. But interestingly, there's actually macroscopic quantum effects as well. And these are superfluids. What a superfluid is the exact pressure and temperature of a material, and it'll achieve a superfluid status. Superconductors, which are conductors that are cooled right down, and then some laser and crystal dynamics. So let's talk about the basics of quantum mechanics. So the number one biggest one is that those systems in quantum mechanics have both particle and wave properties at the same time. People call that the wave particle duality. I don't know if there's a slide on that, but what the wave particle duality is they were able to show that shooting a single photon of light through a splitter. So, there's two holes the light could go to. When you shoot it down the middle, it has a split, right? And they showed if you just shot a bunch of light photons one at a time, over time, those light photons formed an interference pattern on the paper. And that's crazy. If I shot a flashlight on the splitter, I would get the interference pattern because I'm shooting millions of photons. But somehow shooting one at a time, these particles behaved as a wave. So that was very interesting. That really talks about the probabilistic nature of quantum mechanics. And another very interesting one is the third point here, is that observers, as we're observers, we can observe the microscopic system without altering its properties. It's like if I'm looking at someone on Facebook, I'm stalking them, I'm not altering that person's knowledge that I'm stalking them, what I'm saying? So I'm not altering their personality, I'm not altering the way they walk through life. even though I'm observing them. But in the quantum mechanic world, imagine we're observing a photon. The moment we observe a photon, that means that a photon left that area and entered our eyeballs. So that just meant that system either lost a photon or gained a photon because we're observing it. So if we're interacting with the system, somehow information has left the system, and so we altered its properties. Of course, in the macroscopic world, we can stare at a truck all day long, and those photons aren't really going to influence that truck's behavior. Okay. So again, classical world, deterministic, quantum world is probabilistic, and only probability of future states can be predicted using laws of force and equations of quantum mechanics. So although we can never see them, we just have to use our theories to predict where the quantum states will be. So we're talking some milestones about quantum physics. So the scientist J.J. Thomson, he discovered the electron, and he described the electron as a fundamental subatomic particle. And so, when I was a kid, no one could really describe to me what exactly electricity was. I thought it was just lightning bolts or something, like thunder. Is that electricity? But the true definition of electricity is a flow of electrons. So in the same way, like if we said, like, what's a stream of water, it would be hard to describe. But ultimately, a stream of water is a flow of water particles. So the same thing, electricity is just a flow of electrons, flow of all these minus things. This is a very important point. Radioactivity. Very interesting woman. I think everyone learns about her actually. Mary. She's actually one of the only woman to ever receive 2 Nobel Prizes, one in chemistry and the other in physics. And she just discovered that certain elements emit radiation. So wave nature of matter. So this is, people still don't, at this time, people didn't understand that, an object could have both a wave and particle property to it. And so de Broglie, that's what we call de Broglie waves. He is the one that discovered that particles exhibit both a light wave and also a particle property. And the way they did this was they had high energy electrons, and they made the same pattern as X-rays when they scattered from a crystal. And so somehow X-rays, which we know is light, which we know is a wave, made the same pattern as shooting electrons. And electrons aren't waves. Electrons are single particles, right? So a single particle thing, as well as a wave, both made the same pattern, right? So that's really hinting at the wave-particle duality. We're going to skip this slide because it's a bit advanced. But actually, let's not. Let's look at this center image here. We have like A, B, C, D, E. So, this is exactly the wave-particle duality. So in A, the scientists just shot around like 7 or 8 photons, and they seem to be randomly placed, right? The photons are going through a splitter, right? So either the photon goes this way or it goes to the, for you guys would be the right, right? Either goes to the left or it goes to the right, right? So one at a time, the photons either appear there or there. And then at B, they shot, I think 100 photons now, and it's still, they seem to be randomly placed. But then once we reach 1,000, a million of photons, they seem to exhibit a pattern, even though they're as individual photons, they were just going through the splitter, right? But it shows that the moment each photon is released, its destiny almost has a probabilistic value. And that's reflected in E, where we see those distinct field lines. And if you're just shining a flashlight, you'll just a clean interference pattern, just like that. So next thing we're going to talk about is the black body problem. So we're going to get this graph. And so what this black body problem is that Planck assumed that the radiation in a cavity was emitted by some sort of oscillator containing the walls. And so there's some advanced theories here. But the basic idea here is that, like, looking back at this image, when we heat anything hot enough, it starts to glow, right? Whether it's turning on the coil of our stove when it starts, the black body starts to, the black body radiation is when we see like the glow, like the red heat, or when, you know, cars brake really hard, the brakes start glowing. You know, before quantum mechanics, what was hard to understand was the relationship between the wavelength that was emitted and the amount of energy in the system, or, you know, the amount of heat in a system. And so there's some complicated math, but basically this relationship between the color and temperature, the color and wavelength of the black body radiation related to the amount of energy in this metal, that could only, that relationship, that trend could only be described through quantum mechanics. So that's as much as I understand about it. You know, obviously there's already differential calculus involved, which I have no idea about. So yeah, wave particle duality of light. You know, so very cool. Reflection, right? You know, when you're looking at a mirror, waves can do that, particles can do that. Refraction, which is when particles go through an object, so through a window, you know, obviously waves can do that, particles can do that. Interference, right? Like when you throw a tennis ball, it's not going to interfere with your signal, right? Or your radio, but opening your phone near an airport could interfere with the pilot's plane, right? So only waves can do that, particles can't do that. Diffraction, which is when waves go through really tiny holes. Like, for example, all our CDs, you know, they're not just solid pieces of plastic. All the CDs have millions of holes in them, and that's diffraction. That's why when, you know, light hits our CDs, we get a rainbow effect. That's a diffraction. Particles don't do that. They'll just go through the holes. Polarization, which is, you know, if you've seen a image of electromagnetic rays, which is just a cool name for light, you know, it's one direction this way and the other direction this way, right? So it's like they're both 90 degrees from each other. So all waves have like a polarization. You know, that's why there's like polarized sunglasses. If you take two of them together and you shift them 90 degrees, it just really causes complete darkness. Particles don't have this. They're not polarized. Particles aren't polarized. And interesting, the photoelectric effect is a particle thing. And what the photoelectric effect is that this is something Einstein discovered, that when you shoot light at a metal, it will release electricity. I think that's crazy. You know, it wasn't a wave thing. And the reason it wasn't a wave thing is because Einstein was able to release individual photons at the metal, and the metal released the same amount of energy electrons out. So I think it's crazy that, you know, shining a flashlight at the metal released electrons, you know, caused electricity to happen. Right. So I mean, I can read you the what's written here about the photoelectric effect, but it's exactly what I just said, which is the metal plate absorbed light energy in the form of photons, and this excited the atoms in this metal to release its valence electrons. Right, so here we go. So the reason why this is a quantum mechanical effect is, you know, we talked about quantum mechanics being discrete, right? It's not like infinitely small. There's discrete, which means there's finite layers, right? It's like on a ruler. It's not just like 0 centimeters. It's 1 centimeter. It's like increments. And so for the photoelectric effect, it's kind of a yes or no. It's not like in between. You can't release half of a electron. So you have to reach the right amount of light energy before at least one electron is emitted, right? You can't release 1.5 electron, 1.25 electron. It's 1 electron or 2 electron. And so that's called quantized levels, and that's called discrete levels. And that's why it's this photoelectric effect is a quantum effect. So there's a Heisenberg uncertainty principle, very common saying, which is we can only really know either the position or the momentum. And momentum is just mass times velocity. So really momentum means like it's velocity. So either we know where it is or we know how fast it's going, which direction it's going. We can't know both at the same time. So the more precisely the position is determined, the less precisely the momentum is known. Right, we're gonna skip this slide. Right, the structure of the atom. You know, we were talking about this earlier, you know, the Rutherford atom model, where it's this really cool, you know, multi-semicircle, like a planetary system. You know, scientists we always come up with new models and theories to describe what we know right now. And oftentimes these models only work in very tight, specific areas. And that's not good because, you know, we would hope to have one model of the atom that works every single time, not just at one small moment. And so, you know, looking at the Rutherford model, he's saying these electrons rotate around like planets, right? But the thing is, using classical physics, if they were to constantly radiate around, they would lose all their energy, and eventually they would not be fast enough to keep spinning around, and then they would fall into the nucleus. So obviously this model not that good if that's how it describes an atom. And so this is the Rutherford model, and then the Niels Bohr model, you know, explain that it's actually energy quantization at every level. So, you know, Rutherford's model looks like every electron's at the same radius of rotation. But Niels Bohr said that there's actually quantized levels. Right, so what's line spectra? So line spectra is kind of the ladders of energy. So again, it's not infinite details of energy. There's always like discrete levels of energy. So what is this line spectra and absorption? So this is, if I were to shine a flashlight at this atom, you know, we have this atom that has like x equals 4, 3, 2, 1, 4 layers of electrons. If I were to shoot a light at this atom, it's not going to steal, quote unquote, every single wavelength of light. It's going to take select wavelengths. So it's going to take the red, the green, and the blue, right? So that's what absorption spectrum is which specific wavelengths will absorb. And the reason it absorbs specific wavelengths is because the electrons are placed just so that they only absorb at that specific wavelength. Again, such a quantum mechanical property. Right, so atomic spectra, absorption and emission. So absorption is again shooting light at an object and seeing which wavelengths it absorbs. Emission is which wavelengths does it emit. Right, so spectroscopy, you know, very interesting. I think, you know, we learned in I think, yeah, organic chemistry, you know, like these objects have NMR, and this is because, you know, the atoms and their bonds are vibrating. You know, they could either be, you know, stretching, rocking, twisting, wagging. There's so many things, and spectroscopy is really used. Spectroscopy is basically fingerprinting, but for molecules. And this is known as a quantum mechanical effect spectroscopy. Okay, now we're going to move on to the first postulate of quantum. There's actually, I think there's 6 of them. And we're going to skip all the postulates because they're all very advanced and they're not really tested. So, but let's look at the first postulate, which is actually meaningful, which is that all microscopic systems can be represented by a wave function. Okay, so this is a wave function. And you know what a wave function is like, if I were to describe a student at university, their property would be what year are they, what program are they taking, perhaps what age they are, and what department they're from. You know, that's the identity of a student at the university. And that's exactly what a wave function is. It's just one standardized way to describe a particle in the microscopic world. So just as I said, like, I could talk about cars too, like how would I describe a car? The year of the car, the model of the car, the make of the car, the model of the car. That's the standardized way to describe a car. So same way, the wave function is just the standardized way to describe a particle in its quantum state. So we'll skip through all these quantum mechanical things. These are not tested. Right, so I think this slide is important. Just read the last part, which is quantum mechanics, and same with classical physics. All this still fails to explain gravity, right? I think that's very interesting. I don't know if you guys heard of the grand unifying field theory in physics. That's what every physicist is basically trying to do. Because if we think about force equals mass times acceleration, F equals ma, that only works, on a large scale. And then quantum mechanics only works on a smaller scale, right? And so that just means these theories aren't really good enough if they only work at one moment, right? Theories are only good if they work everywhere, right? And gravity is that one thing, no matter if you're in the macroscopic or microscopic world, it always works, right? I think you guys might realize that a lot of our scientific theories are very specific. It's like in chemistry when we have different definitions of an acid. As a kid, an acid was just if it turned the litmus paper red. But then when we grew up, we learned about Bronsted, Lowry acids, Lewis acids, all these acids. And that's just because the Lewis acid model only works in that world. And the Bronsted Lowry acid model only describes acids in that way. And so they're not quite good enough because they only work at their own moments, right? If there was a singular acid model, then we wouldn't need so much models because that one model would work every time, whether it describes why the litmus paper turns red, whether it describes why electrons want to steal protons, stuff like that. So that's the idea of the grand unifying field theory, which is how can we relate everything described in one way and it works every time. So let me read this quote by Richard Feynman, which he's a famous physicist. He won a Nobel Prize, but what people remember him the most was his ability to describe really hard topics like his theoretical physics work to a lay audience. He made a lot of public lectures, and that's really what he's known for. So let me just quote what he said. He said, "What I want to talk about is the problem of manipulating, controlling things on a small scale. At the atomic level, we have new kinds of forces and new kinds of possibilities, new kinds of effects. The problem of manufacture and reproduction of materials will be quite different. I am, as I said, inspired by the biological phenomena in which chemical forces are used in a repetitive fashion to produce all kinds of weird effects, one of which is the author. The principles of physics, as far as I can see, do not speak against possibility of maneuvering things atom by atom. It is not an attempt to violate any laws. It is something in principle that can be done, but in practice it has been done because we are too big. It has not become because we're too big." So, he's hinting at, quantum biology. He's also hinting at, we don't have atom to atom, that kind of control yet. When I was a kid, I thought we could just make gold. We could just put a bunch of atoms together and make gold, but we actually can't do that, unfortunately. And he's just saying because we're too big, we're just not at that microscopic world. So, every model describes a certain phenomena. So how does quantum mechanics apply to nature? What can quantum mechanics help us describe about nature? So, it can help us describe the stability of electrons in atoms, the complexity, quantum entanglement, coherence. These are all just properties that can help describe what we see in nature. Of course, so quantum physics, basis of all modern technology. Of course, everyone knows this, right? Like lasers, cell phones, but if we really think about it, it's very extraordinary. Like I'm sure everyone has a TV in their home, everyone has a cell phone. If it weren't for these scientists that worked on quantum physics, we literally wouldn't have this technology at all. So, most of our advancement in society comes down to scientists that first develop the theories, and only then can an entrepreneur or a business person even make an attempt at making it commercial, right? So I think that's just extraordinary that if this field never advanced, right, it took one person to leave the classical physics, the macroscopic world, and go into microscopic world, dare to discover there, and had no one really dare to go into the microscopic world, we literally wouldn't be able to, we wouldn't be having this call right now, basically, right? So I think that's just extraordinary. And not only like for day-to-day cell phone use, but obviously like scientists use their spectroscopies, MRIs for medicine, atomic clocks, which, sync up all the satellites, all our satellites, X-rays, and then PET scans. So it's really interesting to talk about the dimensions of matter. So for example, an organism has 10 to the 20 atoms, which is like an unimaginable amount of atoms. And as they move down, we really see the scale, right? Like a molecule is 1 nanometer, 10 to the negative 9 is 1 nanometer. And they go all the way down. And the key here is that there's a limit to how small things can get. So, we're down to the neutron, which is something we can still actually see. But then the quark is not something we can see, and that's something that's purely theoretical. Okay. Yeah, again, the scale of biological systems is so interesting. And I think what's interesting is that we assume light to be so small, like the wavelength of light and its photons. But in fact, we look at all these, like E. coli, that's a bacteria, ribosome, that's a protein, right? In our cells, DNA, they're all in the scale of the wavelengths of light, which is very, very interesting. And what this means, of course, is that we can't really visualize a ribosome or a DNA using light. It's unfortunate, actually very fortunate actually, that we get to see the world and our brain, filled in all the colors. Like red is because it's 700 nanometers long, and then blue is because it's 400 nanometers long. Like all our color is like made up by our brain, right? If our brain didn't make up colors, it's just different wavelengths of light. But unfortunately, as visual and beautiful our vision is, we can never see. Sort of chat here. Okay, see you, Darian. Let's close this one. Right. So for example, DNA is so small that light wouldn't work to see it. So we have to use even smaller wavelengths, such as X-rays or electrons, to visualize them, because the wavelengths, light's too big. And to really to talk about this topic, like radio waves, those wavelengths are like 3 meters long. And so imagine you're trying to use a radio wave to look at a person. It wouldn't be possible because the radio wave literally passes through us. Radio waves pass through clouds, they pass through walls. That's why we still get radio reception inside a house, right? And so using that long of a wavelength, we would never be able to see a human or see a wall with such a long wavelength. It's just too massive, right? And so that's the same idea. Like using our visual wavelengths, we can never see very small things. We need even smaller wavelengths to see small things. Then we have biological timescales, which is also very interesting. So looking here, life on Earth at the very right here is like 10 to the 17 seconds, and the cellular events are 10 to 3 seconds. So very interesting that even in biology, the timescales are very different. When neural circuit works very fast, 10 to the negative 2, and then diffusion 10 to the negative 3, and it just goes on that way. Oh, wow, then now there's an energy affinity scale. So obviously, the strongest thing in the strongest bond in nature in a vacuum is an ionic bond, right? So that's between a sodium and a calcium. No, sorry, sodium and chloride, right? That's a salt right there. That's an ionic bond. That's the strongest bond there is. But interestingly, when we look here, the ion bond is only the second strongest, right? It's only 60 kcal per mole, whereas covalent is 90. So I just said the ion's the strongest. Now, what's interesting, I never figured this out. I asked the profs, they could never describe this, but the fact of the matter is covalent bonds are stronger in nature because in nature, everything's in water, right? When we talk about nature, talk about biology, everything's a cell. And so in water, covalent bonds are stronger, right? Because the ionic bond, when you put salt in water, the bond breaks, right? The salt becomes Na plus, Cl minus, right? But not in water, not in nature. In a space and vacuum, the NaCl bond, an ionic bond, is stronger than any covalent bond. But we're talking about nature right now, and that's the opposite is true, right? Covalent bonds are stronger. And that makes sense. I mean, we're made of covalent bonds. We're no ionic bonds here, right? If we were made of ionic bonds, whenever water touched us, we'd fall apart. So, covalent bonds really have a place here. This is some hierarchy just to, notice their relationships. Right, so these are some models of biomolecules, not that important, I think. This is very interesting, this number right here. You know, where I is the atomic weight of the universe measured in proton masses and times the age of the universe in picoseconds. So, you know, this number is just talking about the weight of the universe if it was measured in proton masses. And I think that's just extraordinary that, you know, they always say like there's more stars in the universe than sand on Earth. And, you know, this is what this number is really trying to talk about, that there's so many just raw objects in the world that, I mean, for now, no computer could store, who knows in the future. Yeah, so let's talk about quantum mechanics in life. You know, when we think of quantum mechanics, we think of, you know, isolated states. You know, they're always isolated. You know, they're kept cold and isolated. You know, that's what quantum computing is, right? It's always like super cold, super isolated. But then we think of us, you know, as biological systems, very random, disordered, warm, wet. They're basically the exact opposite of what we would want from a quantum mechanical system. So how could it be possible that even we exhibit quantum mechanical phenomena? So let's talk about reasons why everyone just, you know, discounted quantum biology, like completely. Why would we even think about this, right? Life is big, you know, cells, you know, and then quantum mechanics describes photons, which is super small. So that's one thing why quantum mechanics doesn't seem to be relevant. Another one is quantum mechanics works best in cold, isolated environments, but then we're hot, we're active, right? 37 degrees Celsius, super hot. And then life is wet, right? Cells inside filled with fluid, whereas quantum mechanics, they're usually kept in a vacuum, very dry. Life is super slow, right? Like everything takes a very long time, you know, cell division, cell growth, mitochondria, super slow. And then in the quantum events, they're super fast, right? Photons, I mean, the speed of light, that's 300,000 kilometers a second. Life is complex. You know, we have so many relationships, so many different bonds happening at the same time. Whereas quantum relationships, they try to be more definite, right? There's quantum entanglement, obviously. And so, you know, but somehow nature's still able to do all these things. And that's why there's that last line here that says, but nature is the nanotech master, right? Because somehow nature was able to integrate quantum mechanical properties into our biological world. This is just a quick, we'll just ignore this slide basically. Okay, so these are some quantum mechanical things applied to biology. I think it's worth talking about. So what's a superposition? A superposition just means an object in the quantum world can be two things at once. A superposition is basically Schrodinger's cat, because ever heard of that? It was like before you open the box, you don't know if the cat's alive or dead. That's a superposition right there, because the cat is alive and dead at the same time. And and an answer only comes when you observe it, right? We talk about when you observe it, a quantum world, the state, you change the result, right? So when you observe the cat, you decide if the cat lives or dies, basically. So that's superposition. Non-locality just means it's the kind of that saying about you can only know its position or momentum. You can't know both at the same time. So it's non-locality. Entanglement is very interesting, which is that when things are entangled, you can move them. One's at the sun, one's on Pluto. And if you changed one, the other would change instantly. So that's quantum entanglement. Something I completely don't understand, but I think is super interesting because, you know, one of the problems right now we have is we can't really measure the speed of light because you can't completely sync two clocks at the same time, right? Let's say I sync two clocks right here, and then I gotta move the other clock to the finish line, right? Because I gotta click here and then click there when the light arrives. But the moment I'm moving the clock, it's already experiencing relativity, so its time is slowing down. So the moment, even though if I sync it here, I move it away from where I synced it, the clocks are already not in sync anymore. So, if we are somehow able to apply entanglement to a timing system, then we're able to truly measure the speed of light. So yeah, entanglement shows a lot of promise. Another thing is like, we know that information can travel faster than the speed of light, right? But maybe entanglement could be a way where we can make information faster than the speed of light. So I always think entanglement is a very interesting concept. Tunneling, very important, which is because particles exist as a probability and as a wave, it means like a radio wave literally tunnels through a wall to reach us. Like a radio wave literally went through a freaking wall. So tunneling is describing that. So particles, because they have the possibility to also be a wave, they can actually go through solid barriers. And how does tunneling affect us in real life? Basically in our computers, like there's two CPU companies, Intel, AMD, and all of them are always like flexing about going into smaller processings, right? So Intel's still stuck on their 14 nanometer, whereas AMD is now onto 7 nanometer, but there's a limit, right? Every time it cuts by half, but it reaches a certain point where if you go too small of a nanometer, the electrons will literally tunnel through the CPU solid thing itself, which obviously that will completely not be the point of having a computer. So that's how tunneling will affect us. Right, so quantum biology, it's a very speculative field right now. It's very interdisciplinary, of course, because like you gotta, quantum physicists and biologists have to collaborate together. But some believe that quantum biology is the next step to understanding the more of the nuances of the biological world. And so these are some of the areas where quantum physics seems to have helped describe things. So there's quantum biology, there's, it helps describe photosynthesis for sure. Whenever there's light involved, quantum biology is going to be involved. So let's see. So, is quantum mechanics, is it relevant to biology? On a smaller scale, yes. So for example, we have the energy transporter, FMO, in the photosynthetic complex. I'm pretty sure anyone that took biology 30 in high school or had to take, Bio 107, I think we had to memorize some aspect of the photosynthetic pathway. And FMO is definitely in there. And so, this paper described that the energy transport conducted by FMO was a quantum mechanical thing. And then there's, the birds, how are they able to navigate to their two homes, right? One during the summer, one during the winter when they're migrating. How are they able to navigate so perfectly every time, no matter the change in landscape, the change in weather? They always nail it every time, and people think it's because of the magnetoreception. This magnetoreception, using the Earth's magnetic field, which is pretty constant in a bird's lifetime. And so that's a quantum mechanical effect. Let's talk about some physiological quantum effects, which I think is the most interesting to me when you talk about quantum biology. So the light detection in our eyes, very interesting. And the reason why it's a quantum mechanical effect is it's been scientifically proven that we can detect single photons of light, right? The moment anything is detecting a single photon of light, that's a quantum mechanical effect. So our eyes are pretty extraordinary in that sense. And then the second one, very interesting, is the resonance theory of olfaction, so of smell. Most of the time when we think of taste and smell, we think of keys fitting in locks. And if the key fits in a lock, then we taste it or we smell it. But the resonant theory of olfaction talks about how our nose doesn't rely on keys and locks. It relies on the fingerprinting, the vibrations of the molecules. And the unique vibration of molecules leads us to smell that unique smell. So it's because of the wavelength of vibration, not really the key and lock mechanism. So does biological computation use quantum search algorithms? So let's look at this for a second. So, DNA code, we have 4 nucleic acid bases, which is, GCAT, and used for protein synthesis, and they make the 20 amino acids. And if anyone's in biochemistry, certainly you would have to memorize all the 20 amino acids. But quantum search is most efficient when carried out in databases of size, right? So, I mean, basically what this slide is trying to say is that it seems like quantum search, which is a quantum mechanical effect, is applied to our DNA code, basically. So we'll skip this slide. We'll skip that one, or this one as well. So this is another concept in quantum biology, which is the intelligent cell, which is saying individual cells seem to have their own intelligence. So in this case, we have the centriole, and what's a centriole used for? Centriole releases microtubules across the cell, and those microtubules are just train tracks in the cell to transport things or to change the shape of a cell, right? The classic amoeba, which is able to like literally use its blobs to blob around. The blobs change shape because of the microtubules created by the centrioles. And this is just saying when this cell was affected by pulsating light, somehow the centrioles were able to direct the cell and sense that area. And so some suggest that this might be a quantum mechanical effect. So we have centrioles. I'm sure you guys have seen them. They're like octagons. Are these not octagons? How many is like how many sizes is this? 3, 6, 9. It'd be a nonagon, I guess. Right. So a nonagon centrioles usually are drawn like in a cross like that when you draw them in a cell, and they produce microtubules. I mean, in this diagram, I'm just saying like, this is a plant cell, you can tell by its cell wall, and that different wavelengths of light produce different arrangements of these chloroplasts, which was interesting. Chloroplasts migrate to their light sources. So some say cell-cell communication could also be a quantum mechanical effect. So one example is, when unfortunately an individual has cancer, they might get chemotherapy or radiation therapy. And what's interesting is even though we try to target just the cancer cells, inevitably even the surrounding neighboring cells also get affected and get damaged. And some people, they get damaged so much that they commit apoptosis, which is cellular suicide. And some people suggest that this stress-induced bystander effect is a quantum mechanical effect. So in terms of intercellular signaling, obviously for us, we have that radiation thing where if we irradiate one cell, the cancer cell, somehow the surrounding cells are affected. And so that's one quantum mechanical effect. And in terms of animal signaling, it seems that between fish and mice, they're able to communicate with each other and also affect that quantum mechanically. I'm not too clear on this though. Right, and then there's signal amplification. And what signal amplification is taking a very basic raw signal and somehow translating that into a larger thing. It's been amplified. So I mean, looking at this turtle with this single, like with its DNA, this very raw information was able to translate into like almost like one of those very erratic systems where it has like the two joints, and if you lift them here, they start rotating randomly, and then it becomes complete disorder. It's kind of the same thing. Like this one very clean piece of information somehow snowballed into making cells into tissues, into a brain, into a huge tortoise. Like who would have thought, right? And what's important with signal amplification is the tortoise DNA and our DNA. It's at the end of the day, it's still the same structure, right? It's ATGC. Yet when we amplify both of these DNAs, which under a microscope look identical, when you amplify them, one becomes a human, the other becomes a tortoise, right? So that's signal amplification, right? So that's okay. Right, so I mean, I think this is interesting to talk about like quantum theory of solids, which is that when matter is a solid, when it's cold, or a metal, when a metal is a solid, it seems that the solids vibrate coherently over fixed lattice points. And so this organization is thought to be a quantum mechanical effect. So then we have the heat capacity of solids, which is very interesting. It seems to change. So at low temperatures, the heat capacity is roughly the cube of its temperature. But at high temperatures, it's completely a different model. So this is when we talk about the black body radiation, we talk about when things get very hot, they start glowing. This is the quantum mechanical thing, which is that the heat capacity of a solid seems to change non-linearly at low temperatures compared to high temperatures. The assumptions are that, vibrational motions decouple from each other, and then all atoms in a crystal should vibrate independently, right? But what actually happens is that they're not independent. They're all fixed in a lattice. So this is a very interesting thought. Okay, so it's actually very interesting. So the how do you say this? Sorry, he spelled it wrong. The respiratory is a form of combustion, right? So everything we eat, whether we're eating a piece of bread, a broccoli, all of it, we're just burning it, right? That's why we measure in calories. How do they measure the calories of an item? They literally put it in an isolated box and they burn it and they see how much energy is produced. So we're all burning things. That's how we get our energy. We're just burning it, like lighting a piece of paper on fire. But the reason we don't have to do it at like 1,000 degrees Celsius is because we have enzymes, and enzymes can lower the temperature of a reaction. Reactions happen. The rate of reaction is directly correlated with the temperature, right? Obviously, we can't afford to exist at 1,000 degrees. So enzymes, they lower the temperature for us by making the reactions happen faster. So we don't need to increase the temperature. And so we'll just talk about some relationships with energy consumption of an organism and quantum mechanics. So here they basically describe an interesting relationship. So they're able to make a formula, which is the metabolic rate is proportional to the body size and then proportional to the taxa of an animal, and then by its scaling component. So what's interesting here is that there seems to be a pattern of metabolic rates compared to the body size. So it would seem that the bigger the body size, the larger the metabolic rate. But it's also dependent on the taxa. So if you look here, like plants and animals, very different. So plants have a larger scaling component compared to an animal. So yeah, what's a reason why there's a different scaling rule, right? So looking at the beta here, animals at 3/4, plants at 1. So 1 is a variation in proportionality constant, some people think. And another is a variation in the scaling component, right? But nonetheless, metabolism is important in all life forms, right? At the very beginning, it was just bacteria, and they were conducting mitochondria-like functions in their cell membrane. And eventually there's like the bacteria hypothesis where one engulfed the other. And that's how we get chloroplasts and mitochondria. So here are 3 phenomena that can really only be explained by quantum mechanics. So number 1 is the chemio-osmotic coupling between electron transfer and ADP phosphorylation, right? So do you remember like that turbine that combines an ADP and a phosphate, not phosphate, just a raw phosphor atom combined together to create ATP, that turbine. So people think that coupling with the electrons, right, that pull in the photons, that's a quantum mechanical effect. Another one is the storage of metabolic energy in the vibrations among cellular components, right? So, heat is to describe heat is basically how fast something's vibrating, the kinetic energy of something. So the way some people think that we can store our body heat, obviously a bear when it's hibernating or it's in the winter, it stores its heat through lots of layers of fat, right? And so people think, how does a layer of fat store heat energy? It's because the layer of fat's able to maintain its vibration, and that's storing thermal energy. And then again, quantization of energy. Quantization means discrete levels of energy stored at the membrane. And how discrete? Discrete to the point where we can get individual ATPs, right? The electrons are such that they directly cause a discrete level of energy, which in biology is the ATP. So again, looking here, these are just the quantum mechanical phenomena that happen at the layer of the cell, at the cell membrane. So here's some assumptions. I don't know if we should go too in depth here. But this is something I think people that in biology know, like the plasma membrane that was in a unicell, the most basic cells before there was mitochondria, chloroplasts. All these metabolisms happen at the plasma membrane. And then, once one bacteria engulfed another bacteria, they got a chloroplast, and then that happens at the thylakoid membrane. The thylakoid membrane in the end is still the plasma membrane of the original bacteria. And same is true for the mitochondria. The inner membrane of mitochondria is still just the plasma membrane of that bacteria that was engulfed. Okay. Right, so oxidative phosphorylation, this is talking about that first point. So again, the first point, the chemiosmotic coupling by Mitchell, 1970, that's just described here, right? That going through all these electron centers, they're pumping protons, H pluses. And this is somehow coupled with this purple thing, this turbine, that combines this pumping of protons with making of ATP. So that people think is a quantum mechanical effect. Okay. So we're gonna skip through some of these. I think this is very interesting, actually. So, we have thermodynamic parameters, which is like temperature, which is how fast something's moving. And we have heat capacity, which is how much heat an object can hold. And then the thermodynamic entropy. So how random, how likely is something to occur, right? How entropic is it? So looking at the population, so a biological standpoint, temperature is reflected in our cycle time, right? All living things have an optimal temperature, and when we reach the optimal temperature, we have the max amount of cycles. Same is true for like heat capacity, which is reflected in our metabolic rate, and then entropic production rate. Just as a note, as humans, we're very low entropy, right? To make a human, it's a very low entropy thing because we're so ordered, right? If we were highly entropic, we would just be scattered, right? All our carbons and nitrogens and phosphoruses would be all scattered, but we're very low entropy. Okay. So let's think of some evidences of quantum coherence. So, these are some scientists that might have hinted at the possibility of quantum coherence in the biological world. So there's quantum beating. Lee 2007 talked about protein environments preserving electronic coherence in photosynthetic complexes. Very obscure things, but it seems to exist. Let's see where we should stop today. Let me just see which slide we're on. Okay, these are all things that are very advanced, and I think only Kaczynski could talk about these. I'll just talk about two more topics. Maybe just one more topic, actually. I'll talk about one more topic that's very cool and important. All these, honestly, super advanced, like definitely not tested. I do want to talk about one thing. It's super, super interesting. It's about microtubules. This is the last thing we'll talk about today, I think. Last thing, a very valuable thing to know about. So when you think about microtubules, we can think of there's three functions, right? Three functions of microtubules. Let's look at this chat real quick. Right. So three functions of microtubules. Number one is changing the shape of a cell, right? Changing the shape of a cell. Number two is offering a railway network inside the cell for things to be transported, right? And what are the trains on this railway network? They're kinesins and dynesins that walk along this railway. Number three is during reproduction, where the microtubules touch the kinetochores of chromosomes and they pull them apart. So those are three functions of microtubules. But some suggest that the microtubules have one fourth function. And I think this is extremely interesting. So here we go. We have the microtubule slides. Right, and this is exactly it. So some people think microtubules have the potential to explain our amazing memory, right? So for example, when we store information on our hard drives, on our USB sticks, it's in ones and zeros, right? But looking at the brain, scientists have a hard time understanding where our memory is, right? There doesn't seem to be where are we storing the information, right? All we have are nerves that transmit signals, right? It's like, how can you store information in a river network? Because the water just keeps floating, right? How are you supposed to store the information? So some people suggest that in each neuron, there's microtubules, obviously, right? Microtubules span the entire neuron. They even go down the whole axon. That's all microtubules. And some people think it's the exact configuration of microtubules that give us our memory. And so changing the composition of each microtubule is exactly what our memory is. So, there's some mathematical calculations here, but some suggest that this is one way we can describe our amazing memory, which is just the exact configuration of microtubules in the centrioles. So that's the last thing I wanted to talk about today. In the next lecture, we'll go more in depth into quantum biology, like just quick examples. Today, a little bit tough because we have to talk about classical physics and then quantum mechanics, and then finally talk about its applications. Okay. Yeah, so Dr. Solez, I think we can stop here today and we can talk about the rest next time. Well, I think you might be muted.
Sorry. Yeah, so any questions from the students?
You guys can ask very broad questions. I honestly don't think you worry about the specifics at all, right? Like it's like literally not important to know the specifics because you guys aren't like quantum biologists or something, right? I think it's important to think of this creatively, like the potential, like how does quantum mechanics apply to us big things, right? What I want you to get away from this lecture is that quantum is a small thing and somehow it's being applied to big things, like we're big things. So I think that's that unique relationship that we should take away from this kind of lecture. Do you guys have any questions? Was there any topic you guys didn't quite understand or want to go more in depth about?
Yeah, there was an amazing variety of subjects today. Also, any questions about the material that I presented at the beginning? All right, I guess no burning questions at the moment.
All right. All right.
It's great.
That's great.
Okay. All right. So, and many people thanking you for the lecture, Simon. So that's
Yeah, no worries. Everyone's got to rush
good.
off. Did we go overtime? I think we went. Did we go overtime or?
Yeah, we went over by 14 minutes, but
Oh
that's not
boy.
bad. Yeah,
Okay.
that's okay. Okay, well, thank you very much, and we look forward to Thursday then.
Okay. Thursday sounds good. Thursday. See
Okay.
everyone on Thursday.
Great. Bye-bye now.
Okay. Bye bye.